much for the opportunity to speak today. I'm very interested to follow on from that talk. I come from a world of disease ecology, which sounds almost identical to eco-epidemiology as a field, but there must be some subtle differences, so it'd be nice to tease those apart. As I mentioned, I've got a veterinary background, and together with a large sort of international group where we're looking at interactions between land use change. Flying foxes, many people would consider them heroes. They connect the pollinators, and so they could connect very fragmented landscapes over very wide areas. Many people would consider them villains. When they live close to human populations, they can be noisy, stinky, and in addition to those sort of amenity issues, they also are known to host a number of viruses which can spread to people and can be highly fatal. So for anyone in the room who's not aware of Hendra virus, it was first identified in 1994 and then subsequently realised that it has flying foxes as a natural host. So it is shed in flying fox urine and can infect horses, and highly fatal in horses. Basically, every horse either dies or is euthanized as a result of this infection. And as a result of over about 62 outbreaks, there's been over 100 horse fatalities, and 7 people have been infected, and of those 4 people have died. Thankfully, none since 2009. There's an outbreak going, just happened within the last week or so in Scone in New South Wales, in what I understand to be the highest density of horses outside Kentucky in the US. So very expensive horses, a lot of panic happening down there at the moment. We know this gives an indication of the range of Hendra virus spillovers, although there's now a drop down here as well. Along the east coast of Australia, certainly within the subtropics, it's highly seasonal, with most but not all of the spillovers happening in wintertime. We saw scattered outbreaks in the late 90s and early 2000s with a really high peak of excretion and spillovers in 2011 and annually since then. Our group is really interested in framing this process in terms of all the barriers, I guess, that a virus or a pathogen has to overcome to pass from the reservoir host through to the spillover host. So, the host needs to be present, it needs to be in a density to be transmitting and shedding the virus. It needs to be released and shed. The virus needs to survive for at least a period of time in the environment. The human or the spillover host needs to be exposed, and that virus or infection needs to overcome that host barriers to infection, so the immune system and structural barriers. And each of these components is dynamic in space and time, and only when all of those conditions line up can we see a spillover taking place. So we, through our research, we are looking at, trying to look at each of these layers to look for where are the easiest or most efficient points of intervention that we actually have the greatest likelihood of preventing spillover. One such intervention could be a vaccine, so to boost the immune system basically of the spillover host. A vaccine for Hendra virus was introduced in 2012. Theoretically, problem solved, let's vaccinate all the horses. Unfortunately, people being people, not everyone wants to vaccinate. And there are issues with the rollout basically, and the uptake has been unfortunately quite low. So this is not a solution to this problem. It can be an individual solution for individual horses, but because it's not an endemic pathogen within the horse population, the herd immunity concept is irrelevant. We're looking at protecting individual horses and the people around them. So to make a big effect, we really need a very high rate of vaccination uptake. So the alternative is looking at the root drivers and looking at the ecological causes of spillover and trying to implement solutions at that level. So that gets to, we instead of victims or villains, we could, heroes or villains, we could consider flying foxes as victims. So the work that I'm going to present here is almost entirely work done by Peggy Eady and her colleagues. She's affiliated with the University of New South Wales and also Griffith University now. She's a flying fox behavioural ecologist. She's been working with these species for almost 30 years and a huge amount of knowledge about the system. And so what Peggy and her collaborators documented is this connection between the loss of key winter habitat for flying foxes, behavioural change of flying fox populations, and subsequently an increased risk of Hendra virus transmission and spillover into horses. So I'm going to run through these very quickly, but I'm putting the next couple of slides up to show that we have data to support it, and would be happy to discuss it in more detail with everyone. So firstly, looking at the loss of key winter habitat. We know that of all the habitat for flying foxes in red, that available in wintertime is very low naturally anyway, just because of the flowers that there's eucalypt species that flower in wintertime. We know that as a result of that, in the past, a lot of the concentration of flying foxes at that time of the year was in southeast Queensland. We know that there's been dramatic habitat loss in southeast Queensland over the last 15, 20 years or so, and that as a result we've seen a reduction in flying fox populations in that area over that time. This has resulted in behavioural change in the flying foxes. So from an evolutionary standpoint and a sort of historical standpoint, we know that flying foxes are nomadic. They follow pulses of flowering across the landscape. With climatic oscillations, every 4 to 5 years there are acute food shortages. We think that the eucalypts go into with a lot of rain, with a La Nina, they'll go into a growth phase rather than skip flowering phases. And so as a result, the flying fox populations scatter across the landscape and fragment, looking for food. When the eucalypts start flowering again, they return to their nomadic movements. What we're seeing now is that this habitat loss, we think, is that a lot of that removement to the return to the nomadic movements is not happening, and we are staying within this sort of efficient state. So the data that we have to support this is what we expect to see during food shortages. Is this sort of each of these dots here represents a known flying fox roost, and the red ones are the occupied roosts. And so these inland roosts here represent those that would normally form during one of those fragmentation events. What we're seeing more recently is that those inland roosts are more frequently continuously occupied in very marginal areas, and within this range we've seen this step change with each food shortage in the total number of flying fox roosts. So those roosts are not returning to the historical roosts over time. The size of the feeding areas as a result is decreasing, and so this is Brisbane and the Gold Coast in the red here. This is 1998. Each of these polygons here represents the foraging range of a flying fox roost, and when we go to 2011, we skip between the two, with the increased number of flying fox roosts in that area, the foraging range of each of those roosts is decreasing, and they're relying more on urban food sources. And this pattern is consistent. This pattern here of this fragmentation is consistent right across their range. Many people involved, but their particular arena, Eddie and Hamish. Thank you.